Hi there, and welcome to another video in my TTD 4044 series. And this is 2026, and I'm using a 2026 version of Autodesk Fusion. And I'm going to show you how to take your laser cut truss and get it to give you a nice little structural buckling analysis like this one right here, so that you can see how your truss is going to behave when it's loaded up. Now, for those of you who aren't familiar with the class, we've got a challenge that we're working on called the Laser Truss Challenge, where we build a truss and we laser cut it out. And there's some specific rules that we're going to be following. We're going to have 3 main nodes with specific dimensions, and we're limited to a maximum of 12 nodes in total. So your 3 main nodes that have to be located at these positions and be that size, plus 9 smaller nodes that, again, subject to the rules in the challenge, you can locate where you need them to be. So let's go ahead and get started by opening up Google Chrome. And when you're in Chrome, you're going to go to trussme.com and you're going to click on go ahead to the analysis to start the app, and you're going to come in here, and you may have to zoom in out a little bit. And if you use the little hand here, you can drag this around, and here you can see the origin of TrussMe. That's your 0, 0 point where those 2 lines meet. And you're going to start by drawing a member, and your first member is going to come in here, and it is going to be 10 centimeters, 100 millimeters long. And that's the separation between your 2 nodes at the back. Now you're going to come 320 centimeters out, 320, yeah, millimeters out this way, 32 centimeters. And I'm going to put some nodes along here. You can't just draw one straight line and then break it up. So you kind of have to come along here. And I'm going to do 8, 8, 8. That'll be 24 in total. And then 8. And look at that. There's our 300 line. There's 320. So zooming in and out, you can see your scale changes down at the bottom. So you want to get your scale something like this. So that comes along like so. Then I am going to draw a vertical support node that comes right up in here. Now you can make it go forward or whatever you want. You can make it whatever height you want. Just for symmetry and everything, I chose 8. And now I'm going to finish that off right there. So there I've got my 1, 2, 3 main nodes. 1, 2, and 3 main nodes, 4, 5, 6, 7. So I've got a few more nodes that I can put into this truss, and I don't have to use all of them. I'm just going to come down this way. Now people are like, how do I get it perfectly in a line right there if I can't draw straight? Well, you know what? Just put that in there and rough out the distances. I want to have 1 node maybe there, 1 node maybe there, 1 node out here, and 1 node down here. Okay, and then I'm going to join these nodes up, and this may or may not be the best design. I'm just whipping this through right here so that you can see how this is going to come through, and going to analyze it all later. And there I've got some nodes in right there, and then I can move the nodes around by selecting the elements of the truss right here, and I can straighten this out just a little bit to give me the shape that I want. And that's starting to come together a little bit nicer. Okay, so you can play around with that and get it exactly how you want. I mean, you can play with this height right up here. There, that's not a bad looking truss. It's something to start with. Now, right now I don't have any measurements on it, so you have to come down here and add some supports. And when you're choosing your supports, look up in this top corner right here. You can see I've got a fixed support or a pin node, and I'm going to add that one right there, and a roller support right down here. Now that means that this one can slide in this direction, but it can't go up or down. Finally, I'm going to add a load to the nodes, and I'm going to come in right here. And since right now we're just looking at half the truss, I'm going to draw that out, and I'm going to make that be 125 straight down. There's 125. If I wanted to, I could just type minus 125 in right there. And so you can see that is pushing down there with half of the total force that's going to be pushing down. We're going to put 25 newtons onto our structure. So that represents 1.25 kilograms or 12.5 newtons coming down right there. We've just used this scale so it shows up nicely. And then we can see our reaction forces here. Well, of course, if I'm pushing down right here and I'm pushing up right there, I have to push down right there to balance out my moments. And so now you can go in there and you can play around with the truss to pick up that arrow, and you can move your members around however you feel they need to be moved. And you've got a truss. So I'll let you design the truss right there. Just remember to count your nodes: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm under the 12 nodes allowed, so maybe I can put another node in here at some point. If I wanted to put another node in here, I'd have to delete this line, draw 2 nodes in there, and then connect them. Remember that you always have to build your truss into triangles to make sure that it is statically determinate, to use the fancy word there. You've got the truss all drawn in here. Now you can come here and you can export this file to a DXF. Okay, and there we go. It's exporting in millimeters. And I'm just going to put this into a folder on my computer. And I'm going to call this TTD 4044 Demo 2026. Okay, now that's a DXF file, and DXF files can come into AutoCAD. So I can pop AutoCAD open right in here, and you can get AutoCAD for free if you've got an academic email account. So you just go to students.autodesk.com and get set up right there. And now what I'm going to do is I'm going to open a file, and if I go to that folder on my computer, where I was in Dropbox, material science, so you kind of got to remember where you're saving all your files. I'm not going to see that right off the start unless I tell it DXF. Most of the time, AutoCAD will be trying to open a DWG file, so you won't see your DXF files in there. You'll just see the DWG files because that's AutoCAD's native file format. But AutoCAD's transfer format is the DXF file format. So if I click in right there, now you can see my file right there. Okay, and there is my truss. Now I can't laser cut that truss, okay, because if I do that, I'm just going to cut along all those straight lines. So I have to do a few things here to make it ready for laser cutting. And the first thing I'm going to do is I'm going to add a circle. So I've got the circle tool right up there, and I'm going to do my main nodes first, and they need to be a diameter of 25. So AutoCAD defaults to doing radius. You can switch it to diameter, but I'm just going to use a 12.5 millimeter radius. Okay, so 25 millimeter diameter, 12.5 millimeter radius. And inside there, you're going to have a 13 millimeter hole so that we can slide a steel support through right there. It's going to be a 1/2 inch steel support. 1/2 inch is about 12.5 millimeters, so we make it 13 so it slides nicely. And that's going to be a 6.5 millimeter radius right on there. Now that I've got that drawn in there, I can copy. Make sure I pick copy those 2 parts. And then if I come in here and I've got my object snaps turned on, I can copy those 2 parts from there to right there. Make sure my object snaps are turned on, and I want to copy them to that intersection right out there. Beautiful. And those are my 3 main nodes. Now, my other nodes coming right around here are going to be, they can go up to 20 millimeters, which seems a bit big. You're trying to build this truss nice and light. They can go down to 10 millimeters. So I'll let you choose what size you want. I'll make small ones right here. And so 5 millimeter radius, 10 millimeter diameter. And again, these are going to have bamboo barbecue skewers pressed into them. So we need a hole for the diameter of the bamboo barbecue skewer. Now, I've got different sizes of bamboo barbecue skewer for you. So I'm going to recommend that you go measure the bamboo barbecue skewers so that you get one that works. Okay, makes your assembly go a lot easier. The quality control on bamboo barbecue skewer dimensions is not that great. So I just made mine 1.9, and I know I've got some little skewers that'll probably fit into that. But again, what you do for that dimension can affect your ease of assembly. So go measure some skewers, try a few things, and see how it works. Your classmates may have some suggestions. So again, I'm going to copy that and move that to each of these nodes here. So there we go. We've got a structure with all of the nodes in there. Now I need to create some dimensions for these lines too, because they're just skinny right here. So for that, I need to flick back to Chrome, and I need to say what's in tension and what's in compression. So the blue stuff is all obviously in compression, because if I'm pushing down right here, okay, this entire structure is going to be bending down like this. I just went down to the bottom corner to find that drag. And you can see if it's moving around that arc, the only way that can happen is if these members are getting shorter. In fact, you can see the roller node right here moving off to the left. So there we go. And as those bottom ones get shorter, well, the top ones need to get longer, so they're being pulled into tension. And these ones in the middle are somewhere in between. So where do I have the greatest compression? That's where I want the greatest meat in my structure. And you can see this member here, this member here, and this member here have the greatest amount of compression in them, like minus 500, minus 470, minus 570. This one's in a lot of compression back here. You can play around with those numbers, because if you drag this around, you'll have a different shape. But seeing as how we've already done our export, I'm not going to do that right now. I'm just going to take a look and say, okay, this is in the greatest amount of compression right here. I'm going to make this my widest member and this my second widest member. So you're allowed to go up to 8 millimeters wide. I'll probably make this one 8 millimeters up here. These three, I think I'll all do 8 millimeters wide. So to get them 8 millimeters wide, I'm going to come back to AutoCAD right here, and I'm just going to do offset. And it's going to ask, how far do I want to offset? I want to offset 4 millimeters. Okay, select object to offset right there. There's my 4 millimeter offset. There's my 4 millimeter offset. Now, obviously, if we're able to get away with lighter members, that's great, because that's going to make our truss lighter, which is what we're trying to do. Okay, now I can come back to trust me. These ones, not quite as much compression. So on these ones out here, I'm only going to make them 6. Okay, so let's come back to AutoCAD. And so I'm going to do offset. Hit escape for exit, do offset again. And it will say how far I want to offset 3, because I'm trying to keep it light. Can probably do it for less. Alrighty, so there we go. Now there are our main compressive members. Now these ones in the middle, they have to hold both tension and compression at times. I know it doesn't show very much, but I'm going to make them fairly light. And so I'm going to hit escape and then offset. And on these ones, I'm just going to offset them 2. So that gives me 4 millimeters wide right there. Whoop, did that one wrong. See, that's not centered right there. Control Z undoes that. Pick that one, put it on that side. Got to stay sharp while you're doing this. All right, now these ones along the top here, they're only loaded in tension, so I don't need as much material because tension won't buckle. So I don't have to worry about buckling, so I'm only going to make these 2 millimeters wide, so I'm going to offset them 1 millimeter to each side. Again, trying to keep it light. Um, and chances are you've probably already done this because this is a fairly straightforward part. And this is what we do to actually get our physical truss. Okay, there we go. Now I've got a truss with a whole bunch of lines on it. Problem is, all of these inside lines right here are still going to end up cutting through everything when I send it to the laser. So I need to clean these insides up a little bit. And so I hit escape to get out of that last command, and I tell it I'm going to trim it. There's a button for trim somewhere, but I learned AutoCAD back in the day when you typed everything in. So I'm going to trim this, and it says, what am I going to trim? And I'm just going to draw a line right up there. I'm going to get rid of all that stuff. And keep an eye on what you're trimming. You've got to get it all. I don't want those little notches right there. They're going to weaken it. Now, right down here, I don't want this section here. I don't want that section there. And I don't want that center line right there. I don't want that. I don't want that. I don't want that. Okay. Now I'm going to go through and do that for all the nodes. There's one other thing that we can do is after you've trimmed, you are allowed to add a little bit of a fillet. So you can type in fillet, and you can set a fillet up to a 4mm radius. Okay. And so what you can do is once you've set the radius, you can come here and click there. Oh, am I not getting that? Select first object, select second object. Fillet. I have to type R for radius and tell it I want a radius of 4. You could do 3 if you wanted. And now, once I've told it R for radius, there we go. I get these nice smooth little bends right in there. Repeat fillet. Your rightmost button is going to let you repeat the fillet command. And sometimes you'll end up with situations like this. You might have to go back and trim up afterwards. There's no fillet available right there. So maybe on that one, maybe on the inside there, it's not going to be worth doing, but a little bit of filleting is good. Now, it's going to take a few minutes to go through and do all of your nodes. So you probably don't need to be watched do all of that. So I am just going to pause my recording for a sec and go and clean up all my nodes. Okay, we're recording again here, and so I've gone through and I've cleaned everything up, and I've filleted some of the corners, not all of them, but that's fine. There is a truss. Now, double check each and every corner to be really careful that you don't have lines running down right here. Oh, looks like I missed one little trim right there when I filleted things. I am just going to trim that back up. You really do have to go over each node and double check carefully. Attention to detail matters both before laser cutting and exporting to Fusion. Okay, so at this point, you could send that off to the laser cutter. What we'd probably do for sending it to the laser cutter is we'd group it all together and then we'd copied it. So when we cut it out, we cut 2 of them so you can actually make the genuine truss. But for sending it to Fusion, we only want to send one of these, okay? So if you've already copied it and pasted and moved around, delete it down so you're only looking at one side of the truss. We're going to send this off to Fusion right now. And to do that, we're going to export it as a DXF. Okay, you can save it. That's a great idea. Save it as a DWG. But if you come in here and tell it you want to export it as, sorry, it's in save. Save as. Come in here and tell it to save it as a DXF. Now, there's lots of different types of DXF you can save it as. We may as well use the latest version of DXF. What's that? The 2018 drawing format, I guess. So 2018 DXF, and save it back into that structure, and just add for Fusion at the end of it so you know which version you're looking at, because you might save it for the laser cutter as well, and that would be the one with the 2 trusses on it. Okay, so you've exported it and that's ready to go in Fusion. So now we're going to pop Fusion up. Now you're not going to have a fancy drawing like that. In fact, you're going to be sitting there looking at Fusion going, wow, this looks so different. So let me show you a few things that are going on in Fusion when I just start a new file. When you start a new file, this is going to pop up right on here, and you're just going to tell it you want a new part design, and your unit system should be the millimeter and the gram. Okay, so make sure you've got that selected and just go ahead and create new. There you go. Now, your files in Fusion end up getting saved over here. These are all out on the cloud. And when you come in, you're going to be looking at something like this. It's going to be mostly empty. So what I did was I created a new project. And in my case, I called it Truss Analysis. Okay, so you could call this TTED Truss Analysis or something like that. And that's just like a file folder on your computer. So you're going to put things into here. Now, this is cool because this is on the cloud. You don't have to put on your flash drive. This is all tied into your Autodesk account. You should see your Autodesk account right up in this top corner right here. And that should tell you a bunch of things about your Autodesk account. Okay, so now we're in here and I'm going to bring your file in. This is sort of a structure of what's going on in your document. And down here, you're going to have a little timeline of all the steps that you do. And that's what makes Fusion so parametric and easy to work on. So if you come in here before we get started, let's just double check. And if you right click here where it says unsaved, make sure that it says change to direct modeling. Now, um, we don't want to change to direct modeling. Okay, if I click on that, it says delete parametric history. We don't want to do that. We want a parametric history. Cancel that, okay? But if you see anything other than change to direct modeling right down here, you want to change into the parametric mode. Okay, so just make sure that that indicates that you're in the parametric mode, that it doesn't say change to that it does say change to direct modeling. We don't want to be in direct modeling. We want to be in parametric. Okay, so we've got that set up. We're in the parametric mode, which means it's going to record all of our information along here so we can go back and edit it or change things if we need to. And in here, your document settings were in millimeters and in grams. And this over here is your file. Now, I'm going to be using my fancy 3D mouse to scroll around here. You can change your viewpoint by coming up here and dragging on the view cube. You've got nothing to look at right now. Let me just come back over here and I'll show you moving around when you've got something on here. So here's your view cube and you can drag around in the view cube like that. You can click on a side if you want a particular fixed view. You can rotate around in the view cube. Okay, so you can use that to get particular fixed views of your structure. Okay, that's one way that you can go around. You can use your center mouse button, click on the center mouse button, and you can zoom in or out, or if you press down, you can drag it back and forth. Okay, also down here, you have the free orbit command. You've got a few different commands down here for moving around. And when I pick up on that, I can drag it around like here. I think there's some keyboard shortcuts to get into there. Again, I use a fancy 3D mouse. Okay, so there's some of the interface things that you see going on right here. Come back here, and we're going to start your design by coming in here. And the first thing we have to do is upload your DXF file to the cloud. So under this drop-down menu, come to Upload. Okay, select your files and find that folder. In my case, it was Dropbox, Material Science, wherever Material Science went. There we go. And we're going to bring this up and date modify. Oh, there we go. TTED 4044 demo 2026 for Fusion DXF. So that's the AutoCAD file I just created. Go find your AutoCAD file as a DXF and bring that up and upload. Okay, now that should be coming in somewhere in here. Should come into my truss analysis. And when I double click on that, okay, so once that's uploaded, that comes in right here. And now this is represented as a sketch. Now the sketch is a 2D representation of things. Fusion turns sketches into 3D objects. And when yours comes in, it should be nice and blue like this, and you should be able to put your mouse over top of your truss, and it should all highlight like that, okay? And that's a sign that you have a nice, clean, and complete outline on your truss. Now, when you've got an object in there like that, you can come in here and we're going to extrude that, okay, to turn it into a real physical 3D object. So you're going to extrude that, okay, and you're going to bring that up 3 millimeters. See how that just popped up right there? And there it's creating a new body. So there's our extrude command. And now using my fancy 3D mouse, there is what 1/2 of your truss is going to look like. Now, once you've got 1/2 of that truss created in there, okay, we're going to come in here and we're going to right click on that. Or sorry, we're not going to right click on it just yet. We're going to come up here and we're going to click on the move copy command. And right on here, we're not going to move faces. You want to move bodies. And that should let you be able to select your body right here, okay? And now I'm just going to pick some standard point on here where I've got my axes showing nice like that. And I am going to tell it how far over I want to move. I can just drag it straight over. No, I can't. You have to do this again. Move copy, select bodies. You select the body at your nice point right on here. Then before you start moving it, turn create copy on. It needs to have that clicked first. That create copy is critical because we're going to move it over. And you've got to be at least 40 millimeters wide, but I mean, you don't want to go too wide. Let's try 50 millimeters wide for our truss. Of course, the wider you make it, the more longer cross members you have and the more it weighs. But on the other hand, you start to gain a little bit of stiffness in some direction. So there's some secret sauce in how you put all that together. Okay, now we've got two parallel trusses because we did a move and a copy command. And now we need to fill this middle up with something so that all of this stays put together. Now, before I do that, okay, I'm going to make my life just a little bit easier by coming in here and creating a sketch. So you click on the Create Sketch button and then come and click on this face right here. Okay, and that moves in there, then drag this around, and just for this one node, zoom in on the node where we're putting the load and draw a little flat line along the bottom. Now make sure that it clicks right to this edge, okay, and make sure that when you draw it that it's perfectly horizontal. Okay, you'll get a little mark like that right on there. I'm just going to say finish sketch right now. The reason I want that is so that I've got a flat mark when I put my load on there so that I know it's easy for me to make the load go down. So that was create sketch, zoom in on that end node and draw a flat line, make sure that's horizontal and that clicks to each edge. Because what we're going to do right now is we're going to do an extrude and we're going to extrude each of our nodes. So you see I'm coming along now. If I accidentally click on that structure, I don't want that. Just click on it again, it'll disappear. I just want to come in and get each of my nodes. This is a little bit of a shortcut. It's not perfectly accurate to our drawing, but it's close enough. I've got all of them highlighted. And now what I'm going to do is I'm going to extrude them, not a distance, but to an object. So I was in the extrude command. I was clicking on the profile that I wanted to extrude, which is all of those little holes. And I'm going to go to object. And then I'm going to come over to this side of the truss and click right there. And you can see now everything is joined together and I have a 3D truss. Yeah, it's frightening that solid modeling is actually that easy. And then our simulation is also going to be super easy, which is also really, truly amazing. Okay, so we have this right in here. You know, we should hit save at this point, okay? And let's just call it TTED 4044. In my case, this is a demo truss 2026 version, but you might call it whatever you're calling your truss. Okay, so we've got that saved in there. Now we need to do a few more things just to make the truss a little bit more real. We need to come in here and we need to assign it some properties. So if you come up here under bodies, you'll see that you have body 1. And when you click on it, that's your truss. You could change its name to say truss if you wanted. Right now, we're just going to right click on it. We're going to say physical material. Okay, and when you say physical material, this will pop up right in here. And if you come down to wood, you'll see a whole bunch of different woods that you can use. And we're just going to drag medium density fiberboard. I just clicked on MDF right there and dragged it right onto there. Now, hit close. Now that's going to tell me some things about if I come back to body, okay, and I come in here and I go properties. Properties go on body right in there, properties. I get a menu that pops up. It tells me its area, its density. It also tells me its predicted mass. Now, obviously, these cross members are messing us up a little bit because we're going to be using bamboo, but that's probably close enough to the MDF density for me to think that I'm probably close to about 51 grams. Um, Yay. Okay, it also tells me other information, but this is a way that you can get an estimate of how much that truss is going to weigh. It knows the density of MDF. Uh, we estimate that there's bamboo barbecue skewers are small enough, and then we calculate it in right there. You are correct that you're not going to have to account for this weight right here or that weight right there. Um, I'm sure you can change your model if you're that detail oriented to get a perfect mass pickup. Now, the thing that we can change about our body right here is that when we come into physical material again, you'll see that when we dragged it over, medium density fiberboard popped up right there. And if I right click on that, I can come in to edit my medium density fiberboard. Okay, and we can come to advanced. And under advanced, we can do all sorts of things. We can play with the appearance and change its color around if you really want. Let's make it Pantone color. There we go. Looks more like MDF. You don't have to do that. It has no benefit to the simulation, but it's kind of cool that you can. What we want is your physical and specifically down here, mechanical properties. And we spent some time in class talking about Young's modulus for a material and how that's really important to your buckling calculations. And in class, I showed you some ways that you could measure the Young's modulus of MDF. And unfortunately, I took my samples from two different pieces of MDF. So I don't know which one I've got stocked up for you to go in the laser, but we were getting numbers for our hardboard. And I should be clear, we're using hardboard, not MDF. So you can come in here and you can change your Young's modulus, and the more precise number you give it there, the better the results that you're going to get coming out of there. So I'm going to try changing that up to 4.5. That was one of the numbers that we saw in class. Now you're actually going to have to go out and then test your truss, and then you're going to have to see if a real world truss behaves like it does at 4.5, and you might need to tweak that number to get the best possible results. Also, our density, I think, was running a little bit low when I look at my research on the material properties of MDF, of hardboard relative to MDF. The hardboard is more densely packed, so we're probably closer to 9.9 right there, 0.9 grams per cubic centimeter. So we'll apply that, and now we can cancel that. Now, if I come back in here and do properties on my body, I changed that close, there we go. I changed my physical material, I changed the density, so you can see it's updated my mass to account for the increased density of the material. So let's save it one more time. And what's really cool is that when you save it, AutoCAD saves versions. So if I did make a mistake, I can click here and I can go back to version 1 or version 2. I'm on version 3 right now, as you can see. You're ready to move to the simulation. You've got a truss that's ready to go. So come over here and go to simulation. And you're going to do a new study. And there's two studies that we want to do. One is the static stress, okay? And one is going to be the structural buckling right here. And this is often the most critical one. So we'll take a look at structural buckling and we'll create a study. Okay, so there is our truss. It's sitting right in there. We can rotate around. Now we know we've got some fixed conditions, and this is similar to what we did in TRUSME. We're going to come in here and we're going to apply some constraints. Structural constraints, and we want a pinned constraint, and we're going to apply it to that rear node. So you see that rear member lights up, and now that is pinned, and we click OK. That part can't move anywhere. Now, if I come into constraints and do structural constraints, this is a little trickier for the middle one. It took me a while to figure this out. I actually had to go to Autodesk University. It was a rough trip to Vegas to find that out. We are going to use a remote. I tried every other type, but remote is the one we want. Okay, so that was structural constraints. You want a remote constraint. And right now, we can select our target. We want to target that member right in the middle where we're going to have a steel rod running right through there. And you can see right now that that constraint is fixed in translation. So translation means moving. It can't move in the X, Y, or Z axis. But because this is a roller constraint, it's going to be able to move this way. And if you look at your view box right up here, that's going to be the X. So that's going to be free to move in the X. Okay. Your diagram, depending on how you modeled things and imported them, and that might be different, but it's probably going to be X for you. This is also going to be free to rotate. And if you look at this, this is free to rotate about this way around here. So it's free to rotate about the Z axis. So I can say that is free to rotate about X and, or sorry, rotate about the Z. So it can go back and forth this way, and it can translate in the X. Okay, it can't move side to side, it can't move up and down, it can't rotate or twist in other directions. It's pretty much fixed there. And we can click OK on there. And now we have a pin constraint at the back. We have a remote constraint right here that's free to slide this way and free to rotate about right there. Now we just need to provide a load, and we're going to put a structural load right on. Remember we left that little flat spot? I can put that right on there, and you'll notice those arrows are pointing up. I'm going to say minus 25 newtons right there. So it knows that it's pulling down with a force of 25 newtons. There we go. At this point, you should be able to come in here, and under the solve, you should be able to do a pre-check, and it should say the study setup has all the information required. If it doesn't say that, you probably missed something in one of your constraints back here, or maybe you didn't give it a material. Maybe the load didn't stick to it, but you should see something like that on your truss right there. And if it says everything is good to go, then you can come over here and you can tell it to solve. And you can see there's 6 cloud credits here. If you are a commercial Autodesk customer instead of an educational user, you would be paying, I believe that works out to about $6 US for this simulation, because you're going to send this up, and there is a lot of cloud processing going on. So this is going off to a server farm somewhere, and we are going to solve one study, and it's going to take a minute or two, so I'm just going to put pause while that goes to happen. Okay, that came back fairly quickly here, and you can see I've got some results and some color change, and it says that it's solved. I'm going to hit close right here, and you can see that the results that I get are completely ridiculous. If I'm pulling down here and supporting back here, that top will be in tension, and tensile members do not buckle. There is no way that should be buckling. So what's going on, and why is that happening? Well, come down here, and if you look at your results right here, you can see that that has negative numbers in front of it, and that tells me that it's buckling at negative times that load, like you're pushing up on it. Well, that kind of makes sense that that's where it would buckle if you were pushing up on it. That's not the information that I want, and I have not figured out why I can't tell it to only give me positive answers, but you can see that I don't have a single positive answer down here. I mean, I can look at the other answers and I can say, hey, it'll buckle that way or it'll buckle that way. Um, I know where it's going to buckle if I put my weight on it upside down. I don't care about that. Um, I need to get an answer down here that is got a positive number. So to do that, and honestly, there's math behind that that I do not understand. There's a reason they do it that way. I'm pretty sure the people at Autodesk are pretty smart, but what we have to do to get our answers, we have to come over here and when we do our study, right click on here and for your study, come into your settings and we probably need about 30 modes of failure. You can see we had 3 modes of failure before. We probably need to go to 30 until we find one that is in the positive direction because it just buckles so easily in the reverse direction. So I'm going to tell it 30. Sometimes I've had to go up to 60 on here. So I'll try 30. And now that I've set that, we have to come in here, go finish results, go solve, and solve it again. And this time it's going to do more calculation for us. Might take a little bit longer to solve. Wow, AutoCAD's running pretty zippy today, or sorry, Autodesk servers are running pretty hot today. And so I've got my results back now. And now you see it's still giving me buckling mode number 1 as a failure, but I've got all of these other failures right along here, minus 0.57. I'm looking for a positive number. And I don't know why it can't highlight the positive numbers. Now, the good thing is that I've gone past 1. So I'm going to come to a number that's some multiple of the actual load on here. I'm many times stronger than I need to be. Let's see, do I even get up to a positive number right on here? 30, no, remember I said sometimes you have to go up to 60? That's still buckling in the wrong direction. And yeah, that's just a little bit ridiculous right there. So I don't see a positive number in anywhere. So it hasn't failed in a positive and I'm up to my 3. So I'm probably 3 times stronger than I need to be. So I know I could go back and make some changes. Um, let's see right in here. I'm just going to ask it to give me more modes of failure. So I'm going to finish results, settings, and let's try 60 modes of failure. See if we can get it to buckle in our direction so we know what it's actually going to fail at. Okay, so I'm going to solve that. You might be better if you're watching ahead on this just to start with 60 or something like that. There we go, we're solving. Okay, we're complete. We've got some results here. Let's see how strong is this thing. We know it's stronger than, there we go. Oh, it was buckling mode 31 in my case. Now I don't know what it'll be in your case. You'll have a different structure. 3.5 times the load. And you can see right here that's predicting that that's going to be a compressive failure in these members pushing right back on there. So 3.5 times the load. That was a pretty good sturdy structure. That means that one should fail. We gave it a load of 25 newtons, 2.5 kilos. So that one should be able to handle like 7.5, more than 2.5 times 3, 7.5, and another half on there, like 8 point something kilos before it fails right there, which is great. It'll stand up for our tests, but that's not necessarily what we're looking for. Now, as far as handing something in, this is the screenshot that I'm looking for where you show me the buckling mode where it fails right here. But I think we can make our truss a little bit lighter and we can model this. There's some things that are pretty easy to model in Fusion to see if we can make this truss a little bit lighter. So anyway, I'm going to finish the results right there. Okay, now there is one other thing that we have to be concerned about. That shows me the effect on the compressive members because that's the structural buckling failure. You also have to watch for the linear static stress because if you make the tensile members too skinny, they could fail in tension. So what you can do to find that out is you come along here and you right click on the study and you say clone study. Okay, the clone takes your model, takes your materials, takes all of the load conditions, which you keep exactly the same, and then right-click on that study and go to Settings, and we're going to change it from structural buckling to, where are we here? We want just static stress. There we go. So static stress, and we can just click OK right on here. And the static stress study, now we can solve that and just go ahead and tell it to solve. We know our model is good. Okay, and solve one study. And that will run, and we'll wait. And it looks like some results are in. I'll just hit close right here. And there we go now. In this one, where are my results? Did I forget to press go? Started successfully. Why am I not seeing this? I need to come into job succeeded, results, simulation results. Well, this is different. Aha. Okay, this one even gives you some description on what's going on in here. And so this gives us a safety factor. So we gave it our design load right in here. And what we want to see is that these tensile members, you can see we didn't have a problem with the buckling. We have a problem here in our tensile members that right in there, we are below our safety factor, and somewhere we're right down to 2.5. So it's going to fail at half of the applied load. So let's see right in here if I can find one. Let's change our threshold of happiness. You can drag that down, and if you set it to 1, you can see that some of these pieces are just a little bit too small along the top. Now along the bottom, you can see that they're all in the green and the blue. They're like 4 times and 8 times as strong as they need to be for static stress. But these members right in here are going to be just a little too thin. So I need to add a little bit more meat to them, lest they end up falling apart. Okay, so good thing we ran both simulations because we're not seeing the buckling down here, but we are seeing failure in the static stress. You can see anything red is below a safety factor of 1. A safety factor of 1 means it will hold the design load, exactly the design load. Safety factor 4 means it'll hold 4 times the design load. So right along these top members right here, you can see they could do with a little bit more meat. So I'm going to click on Finish Results right here. Okay, so along the top, we need to add some more material. We can probably get rid of some along the bottom right here. Now, how can I do that from within Fusion? Okay, there's a couple of things we can do within Fusion. And so what we're going to do is we're going to go back to our design mode. And one of the things you'll remember that we did when we were copying these two panels apart was we set them to be 50 millimeters apart. I should have been getting a timeline all along the bottom right there. Where's my extrude right there? Extrude right there. I should have been in parametric mode. Change to parametric modeling. Something switched on me while I was working on that. I was telling you we wanted parametric modeling. Anyway, that should have been in parametric all along. Fusion's messing with me here today. Okay, so anyway, if we're in parametric, that would make it easy to swap it back. What we can do right here to add a little bit of material right on to these sides, just to see how much more material we need to do, okay, is we can create a sketch, okay? and I can create a sketch. Um, let's create it right here. And I'm going to come in here and I'm going to tell it that I want to offset. So if I hit O, I don't want to offset a curve. I don't want to chain that selection. I just want to offset this line right here. And I want to make that 1 millimeter wider. Okay, and I'm going to take that one and I'm going to offset it 1 millimeter wide. There we go, that way. And I'm going to click OK. And now what I'm going to do is I'm going to go modify, and I'm going to go extend that line right to there, line right to there, that line to right there, that line to right there. Okay, and those are just dimension lines right up there. You don't have to worry about them too much. And so I could do that anywhere where I wanted to extend anything. Okay, and now what I can do is I can come over here and finish my sketch. So I might do this one here and extend that one up at the top as well. So I can offset right here, 1 millimeter right that way, and offset 1 millimeter. Oh, sorry, why didn't that extend? Offset, there we go, 1 millimeter to that side. It was covering up the OK button. Let me just move that around. OK. Offset that one, 1 millimeter to that side. It keeps covering up that OK button because I'm working in 1080 screen size. I'm used to 4K here. And then I can extend this, modify, extend. You can see there, that just brings it out. It's very important that your corners meet up. That comes out right there. There we go. And now I could do that for that one as well, but I'm just going to finish my sketch right now. And I can extrude that piece and that piece. And I'm going to go distance to object. I'm just going to come around and extrude it to the inside right there. Oh, that only got those two extruded. I should also extrude, nope, not that piece. You can come in here and choose what you're selecting right here. So I'm going to extrude. There's my two selected. Let me turn that off. I'm going to reselecting it. 1, 2, 3, 4, and to object. And then I'm going to select the object right in there. And now I've fattened that up right on there. So that made this side fatter. Then I'd have to spin around to this side right here and create a sketch on this plane right here and do the exact same thing. Now, the cool thing is I can also come in here, and because I can see this line, it just happens to be deep into the page, I can project it into my current sketch plane. That one's not, there we go, it's nice and blue. Okay, so that's come through right there. I can finish my sketch, and now I can extrude that face, that face, that face, that face. And I can extrude them to an object right over there. And now I've added some meat right up on the top. I might have needed to add some right in there, but this stuff down here is all too heavy. So I can also get rid of some of that, and I can do the exact same thing. I can come in here, and if I want to get rid of some extra meat down at the bottom here to counteract that weight, I can create a sketch on that plane, and I can come down here and tell it that I want to come in here and let's just let's move this side down a little bit. Okay, and to do that, I can just, I can't quite just click on there because that was an import. So I'm actually going to have to come in and create a little rectangle, and I'll remove, let's see, you can see that there. I'm at 1 millimeter right there. I can type my dimensions in. I want 1 millimeter right there. Now that's fixed. And then I'll come in here and create a box on this side. Again, 1 millimeter, and that's fixed. I can finish that sketch. I can extrude this face and that face. Now what's kind of cool, I'm going to extrude it to object over here. And now it knows to cut that away from that object. So now I've cut that down and I can see what impact that's going to have on my structural buckling. I could do the same thing on that side if I wanted. So there's lots of things that you can play around with on your structure. And you can see you should be recording everything you do along here in this mode right here, which lets you go back and change it later on. So I could take that and I can go right back to my simulation now, and I can rerun this static stress with the thicker members right along the top right here. And so if I rerun that study, um, I hit solve now, solve that study. And here we are again, and looks like our study's finished and started successfully and job succeeded. And now I want to see the results. So I click to results mode. Interesting. This has just changed. They update Fusion all the time, so this is a slightly different way of looking at it. Aha, look at that. Remember this used to be red all along here and not quite strong enough? Well, now the red has shifted down right here, and so these sections are where I'm likely to fail, so I probably need to beef those up. And where I remove the material back in here, it's still plenty strong. I probably need to go and rerun a structural buckling study so that I know that it's going to hold together that way. So Fusion can give you some pretty good results reasonably quickly while you're sitting at home without burning through materials. Now, the materials we're using in our structure are cheap materials. I really don't care if you do 5 iterations of your truss. But when you think about how we engineer structures, you do not want to build 5 versions of the Portman Bridge to make sure that one of them is strong enough. So when people are building structures that have to work the first time, being able to do structural engineering analysis inside the computer can really help them visualize and know that their structure is going to be strong enough. Now, it still has some problems. Computers solve the problem that you ask them to solve, not the problem that you want them to solve. So if you give the computer bad data, it will give you a bad answer. How do you know that you're giving it good data? Well, in our case, I've simplified the loading conditions. You don't have to worry about wind loading. You don't have to worry about the live loading of trucks coming across here. You don't have to worry about an army coming across and having everybody marching in step and vibrating the bridge all at once. None of those things really matter. You've got one load case to study. We've simplified it down a lot. The other thing that you have to watch for is what is your elastic modulus and what is the modulus of rupture of your material? How strong is this material? If you've told it that the material is weaker than it is, it's going to tell you that you have to use more material than you actually need. If you've told the material is stiffer than it is, it's going to give you a higher structural buckling number than is actually going to happen. So you have to try and get the best numbers that you can to plug into here. And this is why when NASA is launching space probes, they spend so much time running computer simulations. They actually go and they test their simulations against things that they can test to make sure that their model is reasonably valid. So what I'd suggest is after you've got to this stage right here, go back, make the modifications to your truss that you saw here, and go ahead and test it. Test it to destruction. If your structural buckling study said that it can withstand 7.5 or 3.5 times the 2.5 kilo load, try it with 8 kilos on it and see if it does live up to that. And when it fails, does it fail at the location that it predicts? If your linear static stress that we're doing right here shows that it's not going to hold together, okay, go ahead and run a test and see, does it fail right here when you make that uh, actual structure? Because if what's happening in the real world matches your model, then you've probably got a very good model at predicting what's going on. If what's happening in the real world doesn't match your model, then we need to take a look at why so you can improve your model so that you can improve your truss as efficiently as possible. Again, with our trusses, it's really easy to kick another truss out on the laser. But with the Portman bridge, it's not so easy to kick out multiple Portman bridges from a laser cutter. That would have to be a very big laser cutter. Computer simulation helps on the big structure, and this is a way that you can experience and share it with your students. Thank you to Autodesk for sharing Fusion with educators around the world and students around the world. That's a really nice thing that Autodesk does. To my students, good luck with your structures. And if you're somebody else's students and they've put it onto you, I'm terribly sorry. This is this is a great little project. I hope you're having a great time. And we'll be back later with more videos.